Okay, we're back and we're talking about power. Unlimited power, to quote Emperor Palpatine. Okay. Now, I by the way, I got a green pen that actually shows now, so that's kind of cool. Okay, I had one sitting on my ledge over here. In Physics 1, you learned the equation for power. That power is the work done. Okay, is work or yeah, the work done over time. Work done time. Okay. So it's the rate at which work is done, right? Rate at which work is done. Okay. Okay. And how do we find the energy increase from power? Okay. We use this equation to find the energy increase from power. The change in energy is equal to the power times the time, right? And that should make sense because if well, actually, hold on. No, that's not where I'm meant to go with that, right? Or I guess if work is the change in energy, right? Work is the change in energy, then you can rearrange this equation to get that, okay? And you can only use this equation if the power is constant, okay? That's only if power is constant, which in physics C, right, nothing is ever so pretty. So you can only imagine how often you're really going to be using that. Okay. Another equation for power that you learned in physics 1 is P is equal to F times V. Okay, force times velocity, and this is if force, okay, is parallel to velocity. Okay. Only if force is parallel to velocity, right? You can't use this in any other case, okay? Otherwise, you could use this. The other way that you learn it is F times V cosine theta, which is actually the actual equation, and that is actually dot product. Okay, you've learned that. Okay, it's actually dot product. Okay, that momentum is equal to, or sorry, it's power. Okay, because momentum is also p. P is equal to the force dot v, okay? Which is the same thing as saying P is equal to force times V cosine theta, okay? That's the actual equation relating force and velocity. But the actual, like, supreme ultimate equation that actually is the actual final equation for power involves calculus, and it's that power is equal to the derivative of energy with respect to time or the derivative of work with respect to time. Okay? And how you can calculate the work done by so energy increase, right? Energy increase, hopefully you recognize, is just a fancy schmancy way of saying work. Okay? Calculating work from a power function, it's going to be that work is simply equal to the integral of power dt. Okay? Power with respect to time. Okay, here's an example. It's a pretty quick example. A car of mass m is initially at rest at x equals 0 and experiences constant power p. Derive expressions for the acceleration, velocity, and position of the car as functions of time of the car in terms of p and m. Okay, well, I'm going to break this up into 3 sections. Okay, I need to figure out my velocity function, and from there I can actually get my position and acceleration function. So I should figure out that delta E, okay, is equal to p times t. Okay, power times the time that it's applied over. Okay, and that turns into 1/2 mv squared because we're going from rest to moving. Okay, and that's going to be pt. Okay, still on that side. So, right, the change in energy, we're going from 0 energy to now a set of kinetic energy depending on the velocity. So that's how we're able to set that equality up. And if you move things around, okay, so if I multiply by 2 and then I divide by m, I'm going to end up getting v squared is equal to 2pt over m. So what I'm going to do is I'm going to do v, okay, v will be equal to root 2pt over m. Okay, and the whole thing is square rooted. Now, to make this easier for myself, what I'm going to do here is I'm actually going to factor out this t, and I'll show you how I get there. That the v, right? This is really the same thing as saying root 2 times root p times root t over root m. And how you get that is that you can, if you just factor out that root t, which you can do, you end up getting a nicer looking equation, which is root 2p over m, okay, times t to the 1/2, okay? That's your new velocity equation that makes your life really easy, okay? And I love it when my life is easy, okay? Now, to get the acceleration, okay, I need to do the derivative. And this equation, thankfully, is really easy to take the derivative of because you just because now, right, it's just power rule, okay? Bring that in front. And I should get the acceleration would be equal to 1/2 root 2p over m times t, okay, negative 1/2, okay? That's the derivative of that, okay? What about the integral? If to get the position, I do the integral, okay? Well, to get the integral, I just have to do the reverse power rule, okay? And you should end up getting 2/3, okay, root 2p over m times t to the 3/2, okay? And there's no need for a plus c here, okay, because the initial position is going to be 0, okay? So this means that the plus c is going to be equal to 0, okay? So I don't even need a plus c if I don't want to have that, okay? To give you the graphs, right? So you can kind of see how these graphs are trending if you were to put them into like Desmos, right? This graph right here is really funky. How the position graph is going to look is it should be relatively kind of slowly increasing, and then it kind of like that, sort of. Your velocity graph, okay, what that should do is it should be like this, okay? It increases till it hits a point, okay? And then at A, you're going to notice that your acceleration function is going to look kind of like a weird like L shape. Okay, let me see if I can actually, okay? That's going to be kind of how it looks, okay? So it should be a like a inverse root relationship, and you can see that right here, okay? Okay. All right. Now, the final example right here is about a truck. It experiences a net power input. They give you the power function for 10 seconds. So here's what I'm going to do. Sorry, 10 seconds, okay? It doesn't have the S there. I don't know why. 10 seconds, okay? Calculate the work done on the object during that 10 seconds and calculate the truck's speed at the end of the 10 seconds. Okay, so for part one, okay, I'm just going to do the integral of the power function with respect to time, okay? And I actually do need to apply bounds here, okay? So I'm going to go from 0 seconds to 10 seconds because I'm trying to find the work done during those 10 seconds, okay? All right, plug in my function, 40 t cubed, okay, and this is with respect to t. And then I'm just going to do the inverse power rule. So this will become 4. I divide the whole thing by 4. And you should end up getting, right, that work is going to be equal to 40 t to the 4th over 4. And the bounds here are 0 to 10, okay, like we got earlier. This will become 10 t to the 4th. So let's write that, okay. And then let's plug in our bounds, okay? So we end up getting that, let's see, work is equal to 10 times 10 to the 4th minus 10 times 0 to the 4th. And by the way, that part right there is just going to be 0, okay? And you're going to see that this is going to be like a really large number. Your work should be equal to about 100,000 joules, okay? Okay, to solve the second part of the problem, okay, all we got to do now is to figure out the speed at the end, right? I'm going to do the kinetic energy final needs to be equal to the kinetic energy initial plus the work done. And I derived that earlier in like the previous section of notes, okay? But you should also understand that, right? If work is changing kinetic energy, then if you take what you started with and add work, it gives you their new one, okay? Well, the initial kinetic energy, because it starts at rest, is 0, so there's no need to worry about that. So your kinetic energy final, which is 1/2 mv final squared, is going to be equal to the 100,000. Okay. Mass is 8,000, so half of 8,000 is 4,000. So this is 4,000 v final squared equals 100,000. Okay. You can actually cancel out zeros, right? Because what happens here is that you've got, you can get 3 zeros, you can knock out 3 zeros here, knock out 3 zeros here, and so it's really just 4 and 100 is kind of what we're looking at here. You should get that 4v final squared is going to be equal to 100. That ends up being, when you divide the 4 on both sides, that becomes 25. So v final becomes 25. And then, sorry, v final squared becomes 25. And then v final would have to be 5 meters per second. Isn't that crazy to think about? You get these really big numbers and it ends up resolving out really nicely to like 5 and 10 and whatever, right? Everything works out so nicely. Okay, and of course I know these notes are designed by that with that intention in mind. Okay, there you go. That is power. Okay, all right, girl boss it up.